undergraduate in a class that Ivan Sog and I taught. Ling 110, was it? Linguistics 110 was at Stanford. That was a remarkable class. It was a beginning linguistics class, but out of that class came a lot of stuff. Doug, who did Lucine and Nutch and Hadoop, and Sammy Shao did Java. So a lot of software came out of those 20 students or whatever. Doug then came to Xerox PARC, where I was working, to do work in information retrieval, and then made this this tour of the valley, so to speak, that I think he'll talk about. But was at Apple for a while, doing the software that wound up being, what's it called?
Spotlight.
Spotlight, the IR software. Then was at various other places, at Yahoo for a long time, where he did a lot of work in the basic open source software that underlies search. Then Hadoop, which he'll tell you about, which a lot of you already know about, named after his child's teddy bear, is that right?
Stuffed elephant, yeah.
Right. So we go back a long ways. He did learn some things from other than me, I'll allow. And he's a great bass player. He was also, from that class, one of the two players in that class who was a member of the linguistics rock band Dead Tongues, of which I was also a participant, which is still in its 74th version out there playing. They're having a thing on Sunday at Berkeley, at Stanford. So, Doug, thank you for coming.
Thanks, Jeff. So Jeff is underselling himself. He was the singer in the band, and he would arrive on roller skates on stage. So you probably expect that. He probably does a lot of his lectures here on roller skates. So yeah, I'm going to just sort of talk about a lot of different things that I've been involved with. Jeff told me that you'd be interested in most of them. We'll see about that. So yeah, as Jeff mentioned, I counted it 30 years ago. I was in Jeff's class. I was an undergrad. This is the oldest picture I could find of Jeff. I think he's probably was a good deal younger then than this picture portrays him. I might have been a bit older than that, but not appreciably, at that other institution. So I'm going to sort of try to go over some of what's happened since then, and in the course talk about search, open source software, and big data, which is the thing I've been working on most recently. Sort of first starting with search and information retrieval. Right out of college, more or less, I worked at Xerox PARC for a number of years. The Xerox started getting involved in information retrieval because it saw this trend. It saw that documents were going online. Now, the way that Xerox imagined it was that copiers would capture your documents and store them and become sort of electronic filing cabinets, and we'd provide sort of the power tools to help you use your electronic filing cabinets in ways that you were unable to use your paper filing cabinets. And so we were, given the task of trying to figure out what this could look like and imagine various things. I did work on making search faster and more scalable. We didn't have, started with a fellow there named Jan Pedersen, and I were sort of a two-man team tasked with working on this stuff. And we didn't know a lot about it before that, and we didn't have any tools to start with, so we had to sort of build our own, and in the process, figure out how these things worked, and did some work on making search engines respond quickly. Turns out to be an important part of whether they're effective. I think we didn't quite think of it in those terms then, but I think since then there's been a lot of work showing that if you can get responses in substantially under a second, then people will do more searches and they'll find the things they're looking for more often. So speed is actually a part of how of the quality of a search engine. Sort of interesting observation. Another thing we spent a lot of time doing was developing methods of browsing big document collections. We imagined you'd have billions of documents, and you'd want to know what was out there. You'd want to sift through them and organize them. We did this by automatic clustering and try to then characterize the clusters and came up with this big system and all this elaborate stuff and a number of papers about it. And nobody's really ever gone on and done that much. Now you're starting to see a little bit of a revival of that in big data. It was fun work, but it left me a little frustrated. We had one user of the search stuff, Jeff, would play around with the. We had access to all of the New York Times articles that were published for about 5 years or more. We'd just been collecting them, and we built various search engines for Jeff, who was working on usage notes for the American Heritage Dictionary, and he was interested in searching current usage through the New York Times, and there weren't good tools otherwise to give you that kind of access. Today we all have lots and lots of tools to search things like news archives and look for language stuff. It's Jeff's job's a lot easier, but then we had that. So I was doing a lot of research and coming up with ideas that we thought were neat, but it was hard to test them. And I am a sort of systems guy, build software. I don't really know how to do user studies. That's one thing that researchers can do to try to judge the effectiveness of things. We weren't really doing that. We were just sort of inventing things and writing papers about them, and getting the privilege to travel to conferences and talk about them. It was good times. During that period, the World Wide Web started. Around 1990, I think, was when Tim Berners-Lee built the first versions of it. I think 91 or so, he came and actually spent a year at Park and was right just down the hall from me, literally about 4 doors down. And he seemed like a nice fellow. No, nobody was very interested. Larry Macinter was very interested. Yeah, it wasn't very exciting stuff. But eventually I got sort of frustrated and wanted to work on things that people were actually using. And it seemed to me that the potential maybe wasn't in copiers, but was in personal computers, which were then booming. And Apple seemed to be the possible future of personal computers. So in those years, 93 to 96 that I was at Apple, I don't know if you guys know the Apple history that well. Those are some of the years when Jobs was gone, and John Scully was the CEO at the beginning. And anyway, they went through a variety of CEOs, and Apple was, they weren't going out of business, but nor were they taking the world by storm. They were just sort of floundering. That was the days of the Newton. So I ended up writing search software that I was hoping would go into the operating system and make it so that everything on your machine, everything on your hard drive, would be searchable as you added things and so on, and your emails and everything. That was sort of my dream. But it wasn't really going to happen. It became pretty clear at Apple. It did happen, but it was, a good 5 years after I left. They took some of the things I worked on and put them in and became Spotlight. But at the time, Apple was struggling to find a next generation OS. They had a thing called Copeland. I don't know if anybody here heard of Copeland? We got a couple of nodding heads from the people my age. Apple set about to make a new version of Mac OS. There was the original Mac OS that they'd had for 10 or so years at that time, which was dated, needed a revision. They started building their own from scratch. That didn't go anywhere, and they ended up, when Jobs came back, buying this company Next, and that became what is now known as Mac OS X. But this was all before any of that happened, and that's when Spotlight got integrated into the OS. That was a good platform for doing that kind of stuff. So anyway, a little Apple history for you. So anyway, I was still somewhat frustrated that there weren't people using the stuff I was working on. And I went and joined a web search company called Excite. All right, how many of you have heard of Excite? Got a few, okay. Excite was sort of the second biggest web company for a number of years to different companies at different times, and never really took off and ended up going bankrupt in 2000. But it was actually a pretty good-sized player in its day, and it was exhilarating for me because finally we had, at first maybe tens of users searching per second, and over the time of my tenure there, up to hundreds of people a second doing searches, really having some need to find something, using software that I worked on and finding it. I hoped, and it was very exciting to actually watch these things stream by. We would, would just sit there and I could watch for hours. I tried not to because it's kind of a waste of time, but see what people were using and just see that there's this mass of people out there in the world who you couldn't see, but you could see their searches stream by. So I want to talk a little bit more about search. This is my history of search, as other experts in search here who probably have different versions. This is my search history in one slide. So I'm sort of trying to draw this distinction between what I think of as search as we know it, which is a little box with a button next to it that says search, and information retrieval, which has a longer history of a more general area of research. So there's been a lot of research, as mentioned, through the years in how to solve this problem and related problems. A lot of it was like the work that I was doing. I guess I'll call aspirational, in that people had good ideas, they'd evaluate them in sort of synthetic ways, and they'd publish papers, but people weren't really using these systems in a big way. So it was a fun area to do work academically, but it wasn't having a tremendous impact on the world. That changed a lot with the advent of the web. Initially, the way you found things on the web was with directories. Before Yahoo even, there was this thing called the NCSA new sites list or something. So somebody had a web page where every time somebody put up a website, they'd add it to that page. And you'd go look at that page and you'd see what new websites there were today. That was the way you navigated the web. And people who were around the day probably all remember that page, going to it and saying, oh, wow, these guys have a web page now. Let's go look at it. That was how small things were. Then that got unmanageable, and some grad students at Stanford started for fun building a directory, organizing it in a hierarchical structure, all these links. It was basically their bookmarks. They structured their bookmarks, put them up on a website, and published them and called it Yahoo, and people loved it, and it took off and formed a company that's worth billions now. So that was the first stage. It wasn't search at all. It was browsing. Then this, I think he was a grad student at University of Washington, Brian Pinkerton, did this thing called Web Crawler, where he actually wrote software that went out and visited some websites, probably first the ones in Yahoo and on the NCSA page, and pulled them down, and then looked at the pages that they linked to and pulled those down until it got to, I think, millions of pages, like maybe 2 million, I think. I don't know. I don't even know if it was that big. Wasn't a huge thing, and he got some search software from somewhere off the shelf, and he put it up on the internet, and people thought, wow, that is really cool. It opened people's eyes. Wasn't great quality, wasn't huge, but it was definitely changed things, because all of a sudden you could find things that weren't in directories and find them relatively quickly based on typing in searches. Maybe a year later or so, some folks at Digital. Is Digital still around? I don't think they are. They were the second biggest computer company in the world for a long time, and I think they're now gone from the face of the earth. They put up a thing called Alta Vista, which was 50 million pages. I think it's 40. I think they called it 50, but it was more like 40 really, which was massive, huge, unimaginably huge to folks at the time. Again, the ranking quality wasn't terribly good, but if you typed in the words, it would find you pages that had those words on them. And that was, and all of a sudden, it felt like a large portion of the internet was actually in the search engine, which web crawler never quite had that feeling. And so people started to realize this is really important, and everybody started, building search engines. Everybody who was in the web business. I joined this company, Excite. Excite was the first company to have both a directory and a search engine. It's a claim to fame. And we actually were bigger than Alta Vista. We were the biggest web search engine on the web for a short time. And they sort of, search engines blossomed there from 96 to maybe 98. And then people figured, okay, they're big enough, they work well enough, people are using them, we can put some ads on them, works okay. But we really want to have a more encompassing experience. We want to build what were called portals. I don't know how much of this you guys have covered in this class, this sort of history of the web. Portals became the big, hot, sexy thing for startups. And Yahoo started building a portal where they had search, they had the directory, but they also had email, sports, horoscopes, business stuff, your stock tracker, calendars, all this kind of stuff in one place. And the idea was sort of try to take maybe AOL, this notion that you go to one place and you'd really be stuck there and doing all your things there, and they could advertise the hell out of you and make a lot of money. And that was where things were, business-wise, in 98. That was the context that Google came along in. Again, a couple of grad students at Stanford. And they had some ideas about better ways of doing search. They didn't have very many pages indexed. They had a different way of indexing them that turned out to be really effective at finding home pages. For example, one time I did a search engine for the Internet Archive where we took all of the web pages that were on government sites in that year. So they did this big crawl of all of the US government sites. And we indexed them all with sort of standard information retrieval algorithms. And you'd search for CIA, and you'd find a lot of pages that talked about the CIA, that used the word CIA a lot, which was the classic way of doing information retrieval. What you wouldn't find was the CIA's homepage, which is probably what you want. And so it turns out this technique that Google did, which was a big game changer, and I think people didn't recognize it that much, which is if somebody has a link, and there's text in that link, that you should attach that text to the page that the link is to. Does that make sense? Rather than just indexing it it does count as text on that page when you search, but you really want to take it and go and add it to the page that it links to as text. And so within the US government, there's thousands of pages that have the link CIA that links to the CIA's homepage. And if you use that evidence, it's really easy to find out what the best response is for the single word search CIA. And that's a big thing that Google brought to the table technically. They had this ability to find these home pages. If you're searching for obscure topics, you really do want just words that happen to be somewhere on the page. Google wasn't doing any better than anyone else. But they did well in this one way, which was a really common way people were using search. They weren't necessarily using it the way that people, I think, in information retrieval had expected them to, which was to look for topics. Rather, they were looking for home pages for particular things and wanted to find those places as more and more of the world got mirrored into the internet. So Google became very popular, partly because they were better. They did these kinds of searches much better. But I think another big thing that people forget when they look at the Google story is that Google had no advertising. Everyone else had these cluttered sites with ads all over. It was a era when the FTC had not yet established guidelines for how you were supposed to distinguish advertisements from content on the web page. Since that's been clarified, you have to clearly advertise. You have to clearly identify which results on a search page are ads and which are the actual organic content, as they call it. That hadn't happened. So people, when you visited most of the other search engines out there, you felt kind of dirty. You knew somebody was trying to sell you something. You didn't know which of the results you were clicking on were really resulting in a payment and which were actually somebody just trying to help you. And Google didn't have any of that. They were just building a search engine, no ads, tried to show you things. And so they took off and passed everyone else and showed that search wasn't a commodity, it wasn't dead, it was an active area of work. And they sort of became the leader there in 98 to 2000, 2002, somewhere in there. They eclipsed everyone else. Anyway, little side story of web search. So web search isn't obviously the only kind of search that's out there that you see a lot. I'd argue that ad matching is in many ways a search problem. It's highly lucrative. So there's people working on it a lot and focusing on it as a problem in itself. So this is a problem of somebody has typed in a search, and you know some other information about that person, maybe their past searches, where they're from, some other demographic information, and you want to decide what ads to show them that they're most likely to click on, and that will give you the most money, give the advertiser the best benefit. There's a lot of different things that are in balance here, and it is a search problem, but you've got more than one master. You're not just trying to please the user; you're trying to please the advertiser and the seller of the ad space. So it's one of these problems that's fascinating, but it's also just purely financially motivated, which some people like, some people don't. Other things, you've got product search. There you've got there's a lot of things like this where you've got a more structured space. You see this in product search engines a lot. These what they call facets on the side, where you get to choose. You search for hard drive, and then it wants to know. And maybe I'm showing my geekiness too much that I pick hard drive, but what kind of a connection is it? You want an IDE drive? Do you want a SCSI drive? Do you want to, whatever? Pick your favorite interface. Do you want it? What size? And so on. These different parameters of the search, and those are oftentimes populated automatically. The different categories based on what things your initial search match. It looks at the things the categories that it breaks into that are substantial, and shows you those and lets you permits you to, in some sense, browse the space with a little assistance describing the space you're in. That technique's used for more than products, but that's sort of, I think, where it really comes out of. Searching for people, you see, Facebook, LinkedIn, they know some things about you, and they can use that to influence the search. You want to show people who live near you and who have friends in common before other people, so there's a different sort of a ranking and search algorithm used there. There's lots of other kinds of search besides web search out there. It's a pretty active area in industry, and I think there's also probably lots of good research to be done here. So some search software that I have been involved with is this thing called Lucine. Lucine is something I wrote in originally, I think, late 97, early 98 or something, when I wasn't convinced that the internet was going to go anywhere. I thought the bubble was going to pop. I was a couple years early, and I wanted to hedge my bets by having software that I could maybe benefit from someday in the future. So I took some time off work, wrote this thing, ended up the bubble had a couple years left in it. And in 2000, I made this open source. I didn't know anything much about open source. I'd dabbled a little bit years before in making some contributions to some open source. But it seemed to be heating up. It seemed to be a good hot buzzword. And I had some software which I thought would be useful. Why not give it away for free and let people use it? And it's really taken off. This library. It's used by Twitter when you do a search there. It's used by the iTunes Store, uses Lucine. Wikipedia when you do a search. Netflix, Instagram. A lot of folks. There's folks who don't. Google doesn't. Microsoft doesn't for Bing. Facebook doesn't. But there are actually only a handful of folks who are the big major search players end up building their own search things. But these days, more and more, it seems like everyone else bases it on Lucine. So what is a search engine library? Can I erase any of this stuff? I don't know. Have you guys covered? Have you covered search much at all? All right. Let me talk a little bit about that. You can slide the board up. Oh, that's cool. I forgot about those. It's a pretty. The basic thing is you have this thing called an index that you use to make searches go quickly. So normally you've got, this is the model that a search engine has. is you've got documents out in the world which have words on them. And they come in, and that's what you want to find in the end. But what you build to make it possible to find things is you take each word in the text. So let's take, I don't know, pick a word. Let's call it X. That's an easy one to write. And you save for X a list of all the documents that contain X. So let's say there's an X in document 2, then we'd put 2. And maybe it's in 17 and 1054. And then when somebody searches for 2, we can go and find the documents that it's in. Easy for you got another word Y, let's say, and it's in 17 and 2000. And then somebody searches for X and Y, you can take these 2 lists and merge them and find that they're both in 17 and show that as the first result. It's basically that simple. Now, building big lists when you get to billions of documents is hard. It also gets to be more than you can. Even this, which seems pretty quick, gets to be more work than you can do on a single computer in the 10 or 20 milliseconds that you want to be able to return results. So you farm it out and do it on lots of computers. There's a lot of tricks, but it fundamentally comes down to something this simple, with a bunch of tricks layered on top. So having something that's got a lot of those tricks in one place has been useful to lots of folks. And then they can also collaboratively add more tricks and make it work better and better. And there's tricks both in terms of performance, and there's tricks in terms of making the things come to the top that people might want to see. Adding things like location in. You want things, you want to find stores that are near you in addition to stores that have a particular product. There's lots of bells and whistles that get added on. But that's fundamentally what a search index is. All right, I'm going to move on from search to software in general. So again, this is Doug's categorization of the software universe. Other people might do this differently. But these sort of go over the different things that I've alluded to. And I think it's good to realize there are different ways of creating software. So there's research prototypes, which generally don't have regular users. They oftentimes don't get maintained. They get built, a paper gets written, and then they get discarded. So there's not an ongoing body of people around them. There's no community that maintains it. So that's one kind of software. There's what I call shrink wrap software, which shrink wrap's actually becoming a term of the past. But shrink wrap software is the stuff I think about that you download and install, that you buy. It used to be the case you go to the store and you'd buy a box and then you'd install the software, and a year later, maybe 2 years later, there'd be a new version of it, and you'd have to go to the store and get the update and download and install the update. Today we tend to have apps which update more regularly. They still have some of the issues. I'd still generally kind of lump those into shrink wrap, in that it's more work to test software that people install on their own computers, because people have different kinds of computers, and they use them in different ways, and it's hard to make sure that your software works in all those different cases. So it's hard to test and make sure it works, and then once you've got it out there and it's not working, it doesn't work until you can get an update to it, which now even with that getting down to being days, it's still a problem. You still need to do a lot of testing before you put it out there, otherwise you're going to get lots of bad reviews. And it's harder to maintain. You can't really see how people are using it. So anyway, that was effectively what I was working on at Apple, was Apple in those days, and to some degree today with operating systems and so on, is still in the shrink wrap software business, where you ship software out, and it had better work because it's going to be out there for a while. Fundamentally, you might be able to patch it a little. And it's a difficult engineering methodology. And so then the next thing that I wound up doing at Excite was a web service. And this was a lot of fun, because the only installation of the software is on hardware that you control. You get to control it. It doesn't get thrown out onto thousands of different people's computers. It's all on your computers. You can watch it yourself and see how it's running. You can see how people are using it. You can watch every single use of the software and see if there's any problem, and you can fix it right then and put in a new version, and nobody even has to know. So there's this very, very tight feedback loop. So this was for me as an engineer a marvelously better model for doing software. One thing that I learned though is so Excite, for example, went bankrupt in 2000, and I worked with a number of people, bright people, and we'd written a lot of neat software that was well engineered, and it all disappeared down some intellectual property black hole, and I don't know who has the rights to that software anymore. It's effectively gone. If you tried to use it, then probably there's somebody out there who could sue you, and so nobody sort of wants to go near it. I've never tried to find it. Even if the company hadn't got bankrupt, so software I wrote at Apple, say, is dead to me. I can no longer see that software. I can't refer to it. I can't go and read it legally. It's not mine. It's Apple's property, and Apple is very proprietary about its software, and I'm not allowed to touch it any longer. And that's not as bad as having it gone from the earth. It's nice to know that it's still there, and some people get to look at it and use it. But as someone who writes software, it's in some ways like writing an essay, something you're proud of and you work on. But unlike an essay, it's something you keep working on over time, and it's okay to cut and paste good bits from one to another, or to do something very similar. It's more acceptable in software certainly than it is in literature to crib things from here and there. So you miss it when you leave it behind in that world. Open source changes that radically, in that the software that you've worked on, that you've spent time building, you can continue to refer to. Go back and read, grab things from it, continue to enhance through multiple employers. Since I wrote Lucine, I've had 1, 2, 3, 4, at least 4 different salaried employers. I spent a few years working as a contractor, during which time I had about 20 different people who employed me. All of those are software that I can still work on and still see. And so it's a from a sort of selfish perspective, it's really great as a software guy. Some other benefits of open source. I'm going to talk a little bit more about what open source is. I'm sort of alluding to it here. Is that software is given away freely, and so in some ways you don't need to make promises for it because people aren't paying for it. So if it doesn't work, you can sort of say, oh yeah, it doesn't do that. I'm sorry. You don't have to. If you're working for a commercial company and it doesn't do something, a lot of times you have to say, well, it kind of does that. It just doesn't do it the way you expect it to. And oh yeah, it does that. It's going to do it real soon anyway. And you see, there's a lot of pride wrapped up in it, and you're trying to sell it. And that relationship of selling the software, I think, encourages a certain amount of dishonesty about what the software does and how well it does it. Whereas in open source, you can be refreshingly honest about the abilities and lack of abilities of the software, because you want to elicit people's input. You want to elicit their help. You want them to contribute. Last thing I wanted to mention about open source as a benefit, if you're thinking about getting into software at all as a business, is that it's great for your reputation. People look at software that you've worked on, and they can evaluate both how you work with other people, the quality of your work. They know you. You collaborate. You have a group of peers, which is much larger than the company that you might work at, and that's a huge benefit again for employees. There are advantages for employers too, I believe, about open source. So as I mentioned, it's software that's free of charge. Technically it means it's provided as modifiable source code, which isn't really that much interesting to the end users. So it's much more about the relationship between the different people who are working on the software. It does make it free for end users to use, which is awfully nice. A lot of stuff out there that you know today is probably open source. How many people here are familiar with this concept of open source software? All right, everybody's pretty much up on that one. So Linux, which is the operating system behind Android and more and more things these days. That's what I'm running on this laptop. It's what people run in data centers predominantly these days that are running all the web services. Mozilla, the browser, Chrome, Google's browser is also open source, slightly different form of open source. OpenOffice, anybody here use OpenOffice? All right. Android, the phone OS. And there's, as I mentioned, there's different styles of open source. One property is the license. There's a thing called viral licenses. So a viral license is one that says that if you change the software and then let people use it, you have to give them your changes. So you're not allowed to take some software, build some cool product, and sell it and not give out the source if it's under a viral license. That can get, the reason it's called viral is if there's one little piece of software that you want to use that's got such a license, and you want to build something like a phone that's based on that, then it gets really tricky to make sure that that doesn't infect everything, because then nobody can sell any software on it, potentially, depending on how the license is written and how how viral the license is. Some licenses just sort of say, hey, we're giving it away, do what you want with it, whatever. And those those are sort of non-viral liberal licenses. Some other things about open source. Hang on a second, my throat's. So users tend to like it because of the cost. Free is good. The transparency, in that you can sort of see what's coming, see who's behind it. You know that's you're not dealing with someone who's trying to sell you something. The quality tends to be better. I think developers who know they're working on something in public tend to be more concerned about how their software looks. They're producing it for a bigger audience, and so they do a better job. And so you tend to see higher quality software. There's been some studies of this empirically looking at it, and it seems to be true. So a thing called lock-in. So people who use Oracle, the database, find they build their business, they build their their payroll and their inventory system. Their whole company is built around these big Oracle databases, and which they're paying $1 million a year for. And then Oracle comes back a year later and says, "Okay, this year it's $2 million." What can they do? They've got their whole company up and running. It's very difficult for them to rewrite all these systems that their company depends on. They pay the $2 million. And that keeps coming. And that's this notion of lock-in, that you're locked into using a particular vendor software because you've built your business around it, and it's very difficult to change that without rewriting your business, where your business is to some degree software. With open source, you tend not to have lock-in because there's a free implementation out there, and what you tend to get from a vendor, if you pay somebody, is just support for that software. And that if you decide to get somebody else to help you with the software, you're not going to end up having to pay for the software again, because you didn't pay for it in the first place. And so you tend to not have this sense of lock-in. You can keep using it forever without having to pay more, and vendors can't sort of capriciously keep increasing costs. Another thing I already mentioned this to some degree, that the developers like the exposure. One of the things that people in general like a lot is respect from their peers. There's some people are motivated. People in general are motivated by money, obviously. But I think a powerful motivator is what your friends think about you. And when you're working on an open source project, you've got a bigger set of peers. You're collaborating with other people in other places oftentimes. And that gives you this larger set of peers and drives people to want to do better quality work harder, take more pride in what they do. So psychologically, it's more rewarding, and it produces better products. Lastly, it has this notion of a shared cost. If you've got 10 different companies collaborating on something on a single implementation rather than paying 4 different competing vendors, it's a more efficient way to build the software. And it squeezes out a middleman as well as potentially gets everybody to agree on a common implementation, getting rid of redundant work. All right, that's sort of some open source religion. Now this is sort of the open source church that I belong to, is the Apache Software Foundation. So that's where I ended up with Lucine. I've since done a number of other projects, which I'll say a little bit about coming up, that have all been at Apache. I've been on the board of directors of Apache for the past few years, currently chairing it. So I'm an Apache guy. I don't wear Apache underwear, but I could. So Apache is a nonprofit. It has more than 100 different software projects. I think we're up to 120 or something like that, closing in on 150. Thousands of developers. I don't know what the latest number is, but many thousands contributing to the projects there, working together. And what we require at Apache is that each project run itself as a diverse meritocratic community. What that means is that you can't have one company which controls any project. It has to have contributors who are legally independent, or at least, and moreover, actually more important than that, is that when somebody comes along who's not a part of the community already there, that their proposals are considered on merit, not based on where the person is from, but on the merit of their ideas. That you're really building a community around the shared interest in the technology and not in other shared interests. It can sometimes get complicated, but that's the fundamental principle that we try to force projects to behave well and have folks act nicely to one another. So all the contributions are voluntary. So we've got different competing companies that collaborate, and we make decisions by consensus. So if one person in a software community thinks it's a bad idea, then it doesn't happen. You've got to persuade every single person that every technical step you take is a good step for that community. And that's, again, mostly to drive people to want to collaborate and listen to everybody in the group. And it works pretty well. So I say here quality is emergent. And what I mean by that is that we don't, as a foundation, have any top-down technical goals. We're not trying to take any particular areas of software. We're happy to have 2 projects in a very similar area that compete with one another within the foundation. We're happy to have people release software that's crap. It turns out people don't want to release software as crap. What they're interested in is producing good software. And so that if you have these communities which are diverse and meritocratic, they tend to produce high-quality software. So that's what I mean by that. The quality emerges from the process, from the style of operation. And so we refuse to get involved in anything that has to do with sort of assuring quality. That's not the foundation's interest. The foundation's interest is ensuring quality of the community, and the quality of the software and what the software does, we're very much blind to. It's an interesting institution, and it seems to be working very, very well. We have more and more projects joining that are many of them quite successful. We use a very liberal license that's not viral at all. You can take Apache software, change it, and sell it, and we don't have any concern about that. We want people to give back to the project because they want to be a part of that community, because they want to be able to use the future changes. And if they drift away from the community, then it'll be harder for them to get the advantages of the community in the future. And so they do so at their own peril. We don't want to try to force them. And so I also think of it as sort of a carrot rather than a stick. We don't try to have a legal stick to force people to give software back. Rather, we want to have a carrot that encourages them that if they participate in this community, they'll continue to benefit from that community. That's my software religion. It's, I think, only 12 or 13 years old, Apache now, and it's growing at an incredible clip. It's odd to be, it sounds like I have a lot of responsibility being on the board of directors, but if it's all volunteer, you can't tell anybody what to do because you don't pay them. And so it's the board of directors is all about sort of trying to manage fires without, anyway, it's a political thing is probably the best analogy rather than any sort of command and control sort of structure. There's none of that. So now I'm going to move on to big data for a bit. When are we supposed to finish? We got.
Well, we finished at 11.
Okay. Cool. All right. So I've got 3 or 4 more slides, and then I'll wrap up here. So now I'm going to talk a little about big data, which is a big deal these days, which you've probably heard some about. How many of you have heard the phrase big data? All right. You're good Nunberg students. So in 2002, I started a project called Nutch, whose ambition was to be an open source web search engine, to sort of be an open source version of what Google has and what Microsoft has in Bing, that would crawl the entire web. And I was sort of going off this naive belief that that all software will eventually be open source, will be commoditized, and so let's pick something that's huge and very successful and try to do an open source version of that and see where that goes. So if you're processing billions of pages, as I indicated earlier when talking about search, you necessarily have to be distributed, which means you need to have it running on more than one computer. You can, maybe on one computer you could search 10 or maybe even 100 million documents at a rate of, getting searches back in a fraction of a second, which you need to. But you can't do 100 billion documents that way. You've got to break it up and have a bunch of computers all searching different chunks and merging the results together. Same thing with crawling and indexing it. You simply can't store the entire internet on one hard drive or on the hard drives hanging off one computer. You've got to have lots of computers. So sort of went into Nutch knowing that. We've got to be able to distribute the data. We've got to be able to distribute the search, the indexing. All that has to be spread over lots of computers. Which, it turns out, if anybody's studied any computer science, make things crazy hard. If you're writing software on one computer, it's not easy, but it's not that hard because one thing follows the next and things happen predictably. When you've got multiple computers, networks break. They operate at different speeds, and trying to make sense of that is just kind of crazy. And there's been a whole body of work, a lot of research, and figuring out how do you do things sensibly when things are distributed. And basically, things that are very simple when you're running on one computer become very complicated when you're doing things distributed. And it's this huge impediment. It's a hurdle you have to get over. But we knew we had to get over it. So we figured out a way to do it that was pretty simple, but it was really a pain to operate. It was all very, very manual. And we could run it on 4 or 5 computers. We were crawling, I think we were getting up to 100 million or more pages and running on 4 machines and was able to download those and index them and do various things to them. But it was almost a full-time job to keep those 4 machines running and doing this. Around that time, 2003, 2004, Google published a couple of papers about the way they did things internally. And they had built 2 systems that they published, one I think in 2003 and one in 2004. One was about the Google file system, which is a way of taking a whole bunch of computers with their hard drives that are on a network and making it look all like one big file system that was spread across all of these hard drives. And doing it in such a way that if you took any of one of those computers and you put a bullet in it, that no data would be lost, that everything would keep running smoothly, and you wouldn't even hardly notice. So handling this distributed problem and providing something that we all were knew and loved in software, which is a file system, a place you can stick things and come back later and find them. So then a year later, they published a paper about the system called Mapreduce, which was a uniform way of running a computation over data spread out in such a file system. So you want to you want to build indexes like this. You've stuck a bunch of web pages onto these things, and you want to build something like this. It's a couple of step process, and you want to farm it out over all these computers. And this Mapreduce system helped you do that. Another related problem is this one I mentioned earlier of you've got all these pages. Some of them have links to other pages with some text on them. It's called the anchor text. For those of you who know HTML, the A is for anchor. And you want to take the anchor text and you want to associate it with the page that it points to. And when you've got billions of pages spread over a bunch of computers, that's not entirely trivial, but it's a single-step operation in a Mapreduce system. You can, just in one, I'm not going to go through in more detail how Mapreduce works, but it made these kinds of things really easy. And it also gave you this very general purpose platform that automated all this stuff that we were doing manually in Nutch, and made it so that you could easily operate a large cluster doing this stuff, and at any time put a bullet in any computer and things would keep running smoothly. Not that we walk around putting bullets in computers a lot, but there's some, anyway, funny acronyms in computer science. There's one, STONITH, which is shoot the other node in the head, is an algorithm for how you handle disputes in distributed computing. So this metaphor of putting bullets in computers is used in the industry a lot. All right, so then once we saw these papers from Google, me and another fellow, Mike Caffarella, started redoing these, rewriting Nutch to use these methods. And so we cloned the methods that Google described and got those working reasonably well. Around 2006, Yahoo said, look, we're building this web search engine. We're really struggling with these similar problems. We'd like to adopt this software you built in Nutch. We want to be on sort of a distributed file system and MapReduce-based system. Why don't you come here and we'll help you? And so I started working in 2006 at Yahoo. We took those bits of Nutch and we split them out to make a new project called Hadoop. So a side note, a lot of people say Hadoop, and that's okay. I think me and my wife, I think, are the only people, and my son, who say Hadoop. But if you want, you can say it, but you don't have to. It's one of these things my son said it, he named his stuffed elephant Hadoop, and I said, well, that'd be a good name for a software thing someday, and as I'm always looking for those. And I wrote it down on a piece of paper and asked my wife to write it down, and then we swapped pieces of paper to see that we both would spell it the same, and we did. We both agreed that the way that you spelled Hadoop was H-A-D-O-O-P. You put it out there on the web, and everybody says Hadoop. And I don't know where that comes from. I thought that maybe that people who worked at Yahoo would say Hadoop, or no, say Hadoop, and they don't. They say Hadoop. They don't say Yahoo. Anyhow, so that happened in 2006. There's a sort of a general pattern you see here, and I think we see this over and over again. When Google invented this stuff, when I was working on Nutch at Yahoo, and then you see it at Facebook, you see it at Twitter, you see it all the early adopters of Hadoop, and now we're seeing it at companies across the world. Is they want to stop, they want to scale, they want to stop reinventing things themselves. They've got a problem that they can't find things that easily solve it, and they need to process these really big data sets economically. So it sort of was a solution that arrived at about the right time, at the right cost as open source, and it's really taken off. And we see this again and again. You got a big bank, they've got some data, they've got it in a database, and they want to do some particular kind of analysis on it, and they can't do it, and they can't do it. They try using this stuff, and it just works for them. So it's I think the pattern has been there from the start, that it's meeting a need that wasn't satisfied by other things. So I want to look a little bit at the trends that I think are really driving this. Foremost trend, of course, is Jeff declared big data the word of the year, which has given us a huge boost. But one phenomenal trend is the rate that hardware has been getting faster and cheaper for 40 years or so. You look at Moore's law, which says that the number of transistors in a chip is going to double every 18 months. Doesn't say anything about cost, but in fact the cost of chips has not gone up, and so what you end up having is the sort of cost per transistor dropping tremendously. Size of memory chips, size of hard drives, speed of networks, all these things have been seeing exponential growth for 40 years, which is crazy. There's nothing else out there that I can think of that is like that, where we've seen that kind of growth in a technology that long. If you tried to, if you said if transit had gotten faster for that long, you'd be getting to Tokyo in a few minutes. And we're not doing that. Transit had gotten a little faster, but not that much. Architecture, buildings were getting bigger. They're not getting bigger anywhere near that fast. You name it. Nothing else has been like this. Absolutely phenomenal. How much computation and storage you can buy now for how little. And the trends look to be continuing. So this is obviously going to end up changing things. And we've seen that happen through the years as more and more computation gets out into society. But I think now we're sort of at a phase transition in that the big data trend is really the evidence of. So there's, I think, two sort of things that reinforce each other. One is this hardware trend. People can afford to save much more data. They can afford to generate much more data. Every cash register is now a computer. The little scanners that the UPS guys have, all these things are connected and generating data all the time. Every tractor has a GPS on it that's recording everywhere it goes. There's just phenomenal amounts of data being generated. It's affordable to save it. And on the other hand, if you have that kind of data, you can examine it and you can get a better picture of what your business is, what you're doing. And in general, if you can, with increased understanding, you can increase quality. You can do a better job. You can make things more efficient. You can, anyway, in various ways, if you learn more about your business, you can generally improve your business. That's a precursor generally to improving it is understanding it. And this data gives you the better understanding. And so these feed one another. We see more value. That drives the people to save more data as they get more value from it. I think things are really spiraling. Apparently, the rate that data is accreting is even super exponential. It's much faster. People are saving data at a much greater rate than the cost of saving the data, and that's just a function of the fact that more and more of our economy is moving online. That's where we're seeing growth, are in things that are digitized. That's the industries that are driving the economy tend to be ones that are becoming more and more digitized. And so I think that you combine those and you get this phenomenal amount of data. And we needed power tools to really take advantage of it. Some other aspects of big data are some stylistic things in the way that big data works. First, in order to be economical, so if you're economical, you can save more data. If you cost 1/10 the price per byte stored, then you can store 10 times the amount of data. So that's important. Being economical allows you to scale further and get a better picture. It's not just about being cheap. So there's been a move towards using commodity hardware because those are the cheapest kinds of storage, cheapest kinds of processors are the PC parts that have been that are manufactured in vast quantities. That become very inexpensive. Not these exotic things that businesses have been using to store all their data. That they're basically we're buying these Ferraris and they could be using what's a Kia or something. Lots of them and much more effectively. I hope if anybody has a Kia, I'm sure it's a great car. So another trend or another stylistic element of this is that it's generally smart not to try to move your data around if you've got a lot of it. Moving data is expensive. Networks are getting a lot faster, but still it takes a long time to move something. which you really, it's much easier to do, is to move the computation you want to do on the data to where the data is, and try to move the computation out. And this goes against the way things had been trending a lot in enterprise software and big databases. Rather, they'd have these big storage networks, and you'd buy these big database servers, and you'd constantly be moving data back and forth over a very, very expensive network. There's all this exotic hardware to move the data in and out of the database server. In the big data world, we take a very different point of view, and we say, no, don't bother with any of that. Just send the program out to the data as much as you can. Try to never move it if you can. Another thing is this notion of schema on read. So a schema, anybody know? Word schema may mean something to some people. So a schema is a description of a data set. It's a description. Generally, data sets are composed of bunches of records. So you can think of them as like if you're a credit card company, you've got lots of sales transactions. You've got the credit card number, the date, the vendor, the amount, who knows what else, the products. There might be a slew of things. And the schema is that. It's that there's a price, and it's in dollars and cents, and basically describing all these different fields. And a lot of times you have data from different sources, and so a classic problem in databases used to be, as you load data, putting it into a schema that would facilitate the kinds of ways you wanted to use that data. So you sort of restructure it as you loaded it. So, for example, web pages, if you were loading logs of people's visits to websites, you might want to categorize what browser they're using. And there's, I don't know if browsers send these strings describing what they are, and they're these crazy complicated strings, but you can kind of categorize them into, is it Internet Explorer, is it Firefox, is it Chrome, what else, Opera maybe, whatever. There's a handful of them. And so classically at database load time, you'd do that categorization and then just have those categories in your data. So then you could do your queries and try to find out and draw graphs and so on of usage over time by different browsers or whatever you're doing. The problem with that is that it's discarding information. In that if you don't save that entire string, if a new browser comes along, you can't recategorize. And so the approach in the big data world is very much take things in the rawest form you can as they arrive, without discarding any detail, save them in that form, and then go about trying to, as you're using the data, categorize and project things into, so you've got things in different currencies. When do you want to convert it to dollars? Do it later. Is the big data approach. Don't try to find the exchange rate on that particular day, because there might be a time when you care later about what was the actual price in the currency of the transaction, not in dollars. Anyway, so that's a strong trend, and it comes partly from it being that much cheaper to store things. You can afford to save everything, and it's also this notion that you're not saving the data for a particular use that you've already imagined. Rather, you want to save things because it's valuable to your business to have stuff that's about what you're doing. You don't know all the ways in which you might use it, and so you want to be careful not to throw anything away. So you want to support experimental and exploratory work later down the road. And that's now becoming accepted, that's a priority, is supporting exploration. You're not just building this particular pipeline for processing your data to give you a particular graph at the end of the day. You want to permit graphs you haven't imagined yet down the road. Another thing that's somewhat stylistic is this observation that in a lot of cases, having more data will do better than having a smarter algorithm. The most intuitive way I think about this is that more data is like a higher resolution image. And if you got satellite photos and you're trying to find a missile or a guy lying in a boat or whatever you're trying to find from the air, there's no substitute really for resolution in situations like that. Yes, you could try to have really fancy things for finding, and if you've only got 1 meter wide pixels, than trying to figure out things that could be missiles or could be people. But if you can get a high resolution picture, you don't have to mess around with fancy things. You can just say, we see it. We know what it is. So I think that analogy holds for a lot of cases. Holds a lot for a lot of language problems. If you're trying to do spell checking or translation or search, if you get more evidence, then you can just do a better job of the problem. And using more evidence and a very simple algorithm, oftentimes in these cases proves to give much better results than trying to be very clever up front and spending a lot of time developing a fancy algorithm. I could spend more time on that, but I'm gonna keep rolling. Talk a little bit here about Hadoop. Hadoop's really grown up to become the industry standard big data software. So as I mentioned, it's an open source project at Apache, used by a lot of big web companies, but also more and more used by a lot of non-web companies. We've got Bank of America, Visa, Walmart, you name it. It's hard to find a big company that isn't at least starting to use this to analyze data. Surprise to me, over the past couple of years, all of the big players in the software world have jumped on the bandwagon. Oracle, IBM, Microsoft, Amazon, all these companies that you might expect to come up with competing technologies have all said, no, we want to standardize on Hadoop too. So there's really not a lot of competitors left standing for this. If everybody sort of, and I think that's in large part due to the fact that it's open source. It's got this big community. It's got a lot of big players already collaborating. Other people come along and say, do I want to compete against everyone else? And they say, well, maybe not this time. Let's actually throw our hat in the ring too and help out here. So what it is, I already mentioned the storage, the distributed storage. We call it HDFS instead of the Hadoop distributed file system instead of GFS, which was the Google file system, and the Mapreduce, which is the distributed processing of big data sets. It's really getting more and more generalized into becoming what I think of as a distributed operating system. So you can run it on clusters of computers. People start oftentimes with 10, 20 computers, but they run it on up to 4,000 or 5,000 computers. So these end up being big racks. I had a picture of I don't know if you knew that was a picture of a data. Oops, wrong direction. This is what data centers look like. People like to put nice, cool blue lights and glass panels on the front. Sometimes, some places don't. But racks and racks of processors with a bunch of hard drives behind them, all connected by network cables. That's the environment that Hadoop tends to run in. It gives you this reliable storage and computation. So the idea is that because distributed programming is such a pain, you don't want to have people reinvent things. You want to have one implementation that handles that hard part, and then you can build lots of things on top of that. And again, this is very, very much like an operating system, providing storage, providing resource allocation, managing processors and memory, and all these various managing users and permissions. In some ways, it's become like a giant mainframe. In some ways, computation has returned back to having. I think there was a dream that everybody would, we'd have just personal computing, and there would be no centralized computing. That would all be peer-to-peer, and that doesn't seem to be happening, at least not yet. We're moving towards a very more centralized model, if anything, with big data, and it's become this shared platform for tools and applications. So what's coming next? Google has been wonderful. They're sort of the one company that has their own implementation of all this stuff. And they've been doing it for longer than anybody else. They have an incredible number of bright engineers. And they're living a few years in the future, a few years in the big data future. And they send us these messages from the future via these papers they publish. And sort of set me on this path by publishing the GFS and the Mapreduce paper. And they've continued to do that through the years, publish these papers about how they're doing things internally. And projecting along these, we started out with a sort of batch computing model, which, batch just means you've got a huge amounts of data and you want to transform it into some other data set. You've got documents, you want to transform them into an index. And it's this big bulk processing of data, as opposed to very interactive sorts of things where you're incrementally making small changes to a data set and in real time and being able to see those changes reflected. That's not something that Hadoop has been very good at traditionally. But it started to add those capabilities. So Hbase, which came out of a Google paper called Bigtable, is an online key value store. So it lets you, under a key, you can store some value, and you can insert them at a tremendous rate, and you can do lookups, and you see them right away in there. So it's an online thing. It falls into this set of technologies which are called Nosql data stores. It's a big buzzword these days. It comes from SQL. SQL is the query language that's used by Oracle and the classic big databases. And they've had this, again, this very monolithic architecture. It's very expensive with the centralized compute. And anyway, the model I've sort of been talking about is the old model for data computing. And so sort of to rise up against this came this NoSQL movement. We're gonna do something different. Hbase is an example. There's a couple other out there. This thing called MongoDB you may have heard of, or Cassandra. What are some of the other ones? I'm blanking, but anyway. Couchdb is another one. These databases which are much simpler than what Oracle does, but they scale much further. They go sort of at the expense of features that you get scalability. And so they've called themselves NoSQL. It's not generally a great name because people then oftentimes build up things that look like SQL on top of them, and you say, wait, is NoSQL with SQL? That's so I tend to call them an online key value store. And you read a lot of things that people thought that was kind of the best we could do. We had to make this trade-off. We could either scale really big, and you find papers from eBay and people places like this talking about how they've built their systems, and they say, we had to give up some of these database features, transactions, joins, in order to scale. And scaling was paramount. We needed to, our business is growing, we have to do that. And we'll figure out ways to work around lacking those features in our database. Impala is a thing from the company I work for, Cloudera, which does a full implementation of SQL, of that query language. So you can do complicated queries, but it doesn't solve this problem of what's called distributed transactions. So if you want to make changes to two parts of a data set, and you either need, so let's say you're going to move money from one account to another, you have to worry about things crashing in the middle. And you don't want it to have it move it into one account but not take it out of the other, right, if you're a bank. You need to know that either it made it or it didn't. But you're changing two places, and so how do you coordinate that? And that's called a transaction, these making multiple synchronized changes at once. And it's used in lots of places, and it's something that's very hard to do in wide-scale distributed systems. When you get to thousands of processors distributed over multiple data centers on multiple continents, people thought that was impossible. And they're like, well, just figure out a way to get by without it. Google this last fall published a paper about how they figured out how to solve this. And it's kind of cool the way they solve it. They put atomic clocks and GPS systems in their data centers, and they have very precise knowledge that different data centers around the world all know what time it is. And they all agree, they're all doing things at the same time, because there's speed of light delays. You can't, that becomes a big problem in a lot of these. Is not only is there potential failures, but you don't know exactly when things happen. But they can know when everything happens because they can put very precise clocks. And using that as a building block, they were able to solve this problem and be able to perform transactions on these giant databases that span the globe and be able to move things transactionally and pretty efficiently. So it's been a pretty phenomenal path. And when I look at it, I really see that a lot of the things that we initially thought we had to give up, in fact, nearly all the things we thought we had to give up when we left the the comfortable world of traditional enterprise databases, it looks like we're going to be able to replicate in this newer platform, in this big data world. It doesn't look like we're going to end up having to give much in trade for having this scalability, for having this decreased costs of building things on commodity hardware. And we're getting an open source implementation of almost everything along with that, which reduces the costs and ability of more people to use it. So it's a pretty attractive looking future right now. Not something I would have guessed, but I think this trend, so in Silicon Valley and in lots of places, but in Silicon Valley more than most, there are these boom cycles, booms and busts and hype bubbles, and they tend to pop in a few years, and everyone goes, haha, that was just a hype bubble. And to some degree, the web had that, but the web is really here to stay. And there was a little, too much. It was a little frothy there in the late '90s, and there were a lot of companies that weren't very smart, investments. But overall, the web is here to stay. And I think, based on everything I see, there were other trends. There was a thing called push technologies, which happened in the, 97 or 90 so time frame. And it was, you couldn't see, the cover of every magazine was about how push was going to change everything, that things were going to be pushed out to your computer all the time. And there were these startups based around push, and it kind of went nowhere. There've been a lot of things which don't go anywhere. I really think that big data is going to be in more like the web. There could be some investment bubble, we'll see. But the trends that are underneath this stuff of hardware getting faster and cheaper, and providing value to companies and the economy moving online, are really strong. We've got this technology roadmap, which really says that there's not a lot we can't do in this new world. And so I'm very optimistic that we're not going to see at least a technical bubble here. That is all I had for you today. I think we've got, oh wow, we're almost out of time. I went too long.
Thank you. We have time maybe for one question.
Sure.
So Moore's Law relied a lot on transistor size, and then that kind of hit a bottleneck, and then focused more on parallelization. Do you think parallelization will hit a bottleneck?
Question is whether parallelization will hit a bottleneck. I mean, I don't know that Moore's Law has hit a bottleneck in terms of number of transistors per chip. They're continuing to shrink transistors. People have predicted the end of Moore's Law for a long time, almost as long as Moore's Law has been in effect. It could end at some point. Parallelization is another way to avoid that. You have multiple chips, and we're certainly seeing with these sorts of big data technologies is a lot about parallelization. A lot of times parallelized on different computers altogether, but within each computer, you typically got 8 cores or more, and so there's a lot of parallelization there. So I don't think there's a real risk that we're going to hit that. So, but your question was not. Sorry, you had a second part to it.
That was it.
Okay, Jeff.
If you have other questions, Doug will be outside.
Yeah, I'll hang around. I won't keep you longer. Thank you.